Okay, so let's welcome Larsen from the University of Michigan, and we'll talk about thermodynamics of supersymmetric black holes in AdS5. Thank you.
Thanks a lot, and thanks for having me here. Can you make this thing go away, or just like my computer? But
sorry, yes.
Will it go away? It will just go away by itself? No.
If you click on more, there's an option to hide it. Hide floating moving control.
It's for hide float.
Okay. Very good. So now we just need to press escape. All right. So I want to tell you, I expected it to be a broad audience, and therefore I will make things simple. I'll work on a number of different things, but that are interrelated. But the story I'll tell you is very self-contained and quite simple. So it's on thermodynamics of supersymmetric AdS5 black holes. So let me try to decipher that a little bit and to give you an outline of what the story is. So if we can change. Not the mouse. That's hard. So I'm interested in black hole thermodynamics, and what most high-energy theory people would know is that you can compute the black hole entropy by computing the area of the event horizon. And one aspect of thermodynamics, there are others, but one is to study the dependence of the area and therefore the entropy on various parameters of the black hole. So the mass, the charge, and so on. And the simplest example of this is asymptotically flat Schwarzschild black hole, where the free energy, so the on-shell action, looks something like this. It comes up really high and it goes down. In particular, it's positive. The free energy is positive. That means that black holes are unstable. They radiate Hawking radiation. And what they radiate to is to the gas that has, to this approximation, very little free energy, because black holes have a lot of states and gases have not very many states. So to this approximation, they have zero free energy. They also have negative specific heat. It gets pushed out here to larger and larger temperature. So that's the most basic story. That's not the one we're interested in. We're interested in the corresponding problem in AdS space, where there's a little bit more structure. In particular, I'm going to consider black holes in AdS5, the dual to n equal 4 super Young mills and b equal to 4. And that case has a very rich phase diagram. And in particular, it's interesting for many people because it has similarities to physical QCD. There's some similarities. It's not the same at all, but there are some interesting similarities that we'd like to understand. Problem is, it's exceptionally well studied. It's not exactly a novelty to try to look at this problem. Literally 1,000 papers have been written or more. In this talk, I will consider pretty much this problem corner that was not previously studied well. I'll talk about supersymmetric black holes in AdS5. So it's a very standard story. It's a very retro story in that way, but it is, but with a new angle. So it's just a new part of phase space. So let me start just with what is the story there when I say it's rich in the Schwarzschild AdS story. So if you have a black hole solution in the AdS space, then the curve for the free energy looks like what's on top. A little bit more complicated. It has this branch up here. That's the small black hole branch. This means that we have black hole solutions that are in AdS, but the black holes are much, much smaller than the AdS radius, small black holes in other words. So they barely notice that they're in AdS. So therefore, this curve looks a lot like that of the Schwarzschild black hole. They don't notice much that there is an AdS space. But as you go up here and the black hole gets to higher temperature, there simply is a minimum temperature. That's when it departs qualitatively from that of the Schwarzschild black hole in flat space. It's noticed that it's an AdS. And we get to a totally qualitatively different branch, large black hole branch, where the AdS radius is the one that's kind of small, and the black hole is noticing the AdS substantially. So after this cusp here, we get to the large black hole branch. We can think about it as a fluid inside the n equal 4 super Young mills. So we really are now in a phase where we sort of are in a plasma type phase inside the 4D quantum field theory. So that phase here is one where we can learn maybe things about interesting features of quantum field theory in 4 dimensions. even though what we're looking at is actually a black hole. One particularly interesting feature is this point here. As I say, when things are positive, actually the black hole is unstable. It can decay to just a thermal gas in the space, but when we have negative free energy, this is an absolutely stable state. And the point where these meet is the Hawking-Page transition. It's where the thermal AdS gas, so the one that has zero free energy, no longer wins, and it's the black hole that actually is the stable phase. And this point we can think about as a confinement-deconfinement transition, with the deconfined phase being the black hole. It has order n² degrees of freedom, which means that the quarks are fully free to roam as they wish, while this one here is the confined phase, which has order 1 degrees of freedom. So this Hawking-Page transition is one of the big mysteries that we would like to understand in much more detail in this business, and people have, of course, tried to do that. So my angle is supersymmetric black holes. And you might reasonably ask, why are you discussing thermodynamics? Because they do not have conventional thermodynamics. In particular, they're all extremal, they have zero temperature. In fact, their mass is not free to just change. We have black holes here that have charges, Q. They have angular momenta, J. And their mass is just the sum of those different 5 quantum numbers that you have for these particular black holes. So what the thermodynamics means here is not dependence on temperature. There is no thermo in the thermodynamics. It's dependence on whatever potentials are conjugate to these charges and these angular momenta. Because once we have determined those potentials and say what they are, and say what the free energy is as function of those potentials, then you don't need to say what is the energy, or you can't tune the corresponding temperature. There just is nothing to tune. There's no extra degree of freedom. So we don't have that freedom that we might normally have. So this is the phase diagram of the supersymmetric AdS5 black holes. This is actually where we're going to end up a little bit later. Now, the point here is that this, you would notice, looks a lot like the Schwarzschild diagram. But it's not. It is not. The free energy here is exactly 0. What I've written up here is something I call the PPS free energy. And the temperature is 0. So what I've written out here is not T, it is tau. It's an analog of temperature, something that plays the role of temperature. So we need to understand what are the things that play the role of free energy and temperature. They're very similar, actually, to those in the non-supersymmetric case. And then we have to understand, why does that diagram look that way? Why does it look much the same way in the supersymmetric case as it does in the non-supersymmetric case? And in fact, do they look the same? And that's one of the things we'd like to pursue in order to understand in more detail why the diagram is the way it is, also microscopically, because with supersymmetry, we have more control.
So can you,
Yes.
ask you about the previous diagram? So did you subtract the T⁴ contribution for thermal AdS? Because why is it? I'm just why is it 0 for thermal AdS? Isn't there? If you think about this,
but it's not of order n², so it's not 1/g. So you have a number of species, which is about 8, and it doesn't rise like n² in your SUN. So it's some number. You're right; it goes like T⁴, but it's with a number in front that's so small that it doesn't
because
count.
there's no deconfinement.
This is divided by n². So therefore, since an n is really, really big, so therefore it just kills whatever you might have had there.
Because in QCD it would be n² times T⁴ in the deconfined phase, right? So, but here,
In the
because it's
deconfined phase, right?
Right.
But this gas here, we think about it, the confined phase.
it's always in the because it's
The confined phase. So they're only order 1.
yeah. Okay. Thanks.
So it's yeah, so they're 8 or whatever number of degrees of freedom. It's not very interesting. It's true that it has some temperature dependence, but
Yeah.
So
Yeah.
going back here, so in
to this one again.
well, okay, let's start with that one. So here, this downslope indicates instability, right? I mean,
This one here, instability, yeah. So these ones here, they're kind of like Schwarzschild black holes
right?
with some extra AdS thing, but we're not that interested. That seems like a complication that's not particularly interesting to add AdS to this stuff here.
Right. So
Now we add a big time.
Right, but so in your BPS analog,
Yeah.
there's again this similar curve.
There is.
So what does it indicate there?
Well, so that's part of what I would like to explain. Is to where did this one come from? Actually, first, what do these things mean? So, yeah, I'll, yeah, yes?
So after, yeah, kind of very nice, but after the Fourier filtration condition, so does the ensemble of the vector all go to the some radius or still some?
Well, it depends on, I mean, here, what the tau parameter is, right? So that's a tuning external parameter. So everything is in AdS, but it may be that you just have a diffuse gas in AdS, or it may be that you have a black hole in AdS. And in here, there's a competition between the two. They coexist at the same value of tau, but the gas wins. So the black hole can decay, even though it's supersymmetric.
And feel about this confining the phase. I mean, so you don't say that there is another string tension in that phase, and that. So what are these degrees of freedom with describe the confining phase?
That's a fair question. I thought about it with our discussion a bit earlier. That yeah, so I should think about that. You know, I mean, look, this here is a very, very well-known story, and I'm honestly, sometimes it's so familiar that just repeat it on auto. And you're right. It sounds like a very relevant question. But the auto story is auto 1 degrees of freedom, surely it's confined. We're done.
In the sense that you have like n to the 0 and all that.
Yeah, but of course you should ask, no, but surely there must be some Wilson lines, and there's some order parameters here, and yeah, I mean, and there are, and some of that at least is understood. Oops, so the other way. So the actual outline of my talk is that I'll tell you a bit more detail about these non-supersymmetric thermodynamics. Basically, I want to introduce angular momentum and charge and what those things do. And the goal with doing it is, how do we get close to the supersymmetric limit once we have something that's not supersymmetric? That sets us up for discussing the supersymmetric thermodynamics. What is it and how do we think about it? And in particular, at that point, I want to introduce a brand new feature that sort of is a surprise, one thing called the constraint and its conjugate potential, which is called phi prime, but we'll get to that eventually. So for now, I just want to say what is it we actually do, because I want to do a little bit more details. So physically, we have this free energy, G, temperature, electric potential, angular velocities. We could have 3 electric potentials, but I pretty much just set them equal, so there'll only be 1. And also 2 angular momenta, and I sometimes will take them equal and give them no index, and sometimes not. But in practice, the work you actually have to do, or more precisely that your student has to do, is that the physical variables, like these guys here, are a function of some obscure parameters, A, B, Q, and little m. And this little m is itself traded for some position of the horizon. So what you have is some parameters that are obscure. And as a function of these parameters, you have a free energy, function of 4 different parameters. You can easily check that there are indeed exactly 4. You can also check that this looks sort of complicated, but not like insanely complicated. It is explicit. And then you should invert and say, yeah, but it shouldn't be function of these obscure parameters. It should be function of these potentials. So to do that, you have to study the nonlinear dependencies that are well implicit in these formulae by doing parametric plots, and see what actually is the content of these formulae. Of course, we can do some analytical work by taking various limits and so on. But at the end of the day, what we try to do is to tease out what is the nonlinearities sitting inside these explicit but obscure formulae. What are we looking for? Because as you can see, it still looks a little bit complicated. There are 4 parameters. I can give you infinitely many plots. Well, this BPS mass formula that we had is a sum of charges, sum of angular momenta. So I take the charges equal. I have 3 Qs here, so I have a special value of my potential, 3, because there are 3 charges in this system. I also have special values of these omegas. The special values is 1, because the J appears with a coefficient 1 in the mass. And this 1 is not just some arbitrary number, because these omegas are actually angular velocities. So when they go to 1, it means that the horizon goes at the speed of light. So therefore, the omega actually has a maximum. The omega star here, which is 1, is the maximum possibility. And that would be, if it's supersymmetric, we must have this equal to 1. If it's less, well, it's not supersymmetric. So the plan is to see what do the angular velocities do, and then what do the electric potentials do, and then what happens when we go to these special critical values. But these critical values I introduced already in advance, because even if you're not interested in supersymmetry at all, they have incredibly qualitative significance for the non-supersymmetric case. So here's the dependence on angular velocity. The blue curve, omega equals 0, is actually the same curve that I had earlier. It has angular velocity 0. So it is the AdS Schwarzschild. It's the one where we have a Schwarzschild phase that's like small black hole, kind of like flat space Schwarzschild. We have the much more dense phase here that's like a conformal liquid plasma. It competes with the thermal gas. When you turn on angular velocity, well, it looks much the same, but you can't help noticing that, well, the maximum goes up as we increase our angular velocity. The Hawking-Page transition here moves lower. In both cases, we think about that as saying there's a tendency that the free energy increases, thermal gas become more competitive, and the temperature we need to have in order to make it a black hole rather than the gas goes down. In both cases, we get the feeling that it destabilizes the black hole, that once you make things rotate, whatever is happening in this material is that it gets destabilized. Rotation tends to get less stable. What happened then when you, in addition, add potential? These curves are the same as on the previous slide, as in they have the same angular velocities, but I added, in addition, some electric potential. You don't remember the curves on the previous slide, I'm sure, but you might even visually see, these ones, they look kind of smaller. They are. They were done in exactly the same size as the previous slide, and they have been all bumped down. The electric potential at the same value of rotational velocity, it tends to bump down the free energy. In other words, it actually makes the black holes more stable. Once you put more electric potential on, the black holes become more stable. The cusp is lowered, the electric potential is being stabilizing, have a stabilizing effect. So there's a competition between these two different things. What happened now when you go all the way up to the critical potential? Well, then suddenly that entire small black hole branch that was going down and down and down as I increased the potential has entirely disappeared. Once you go to the critical potential, there is no small black hole branch. You only have the large black hole branch. This is still for all the different rotational velocities. So we can think about this one here as being kind of the continuation of where did this Schwarzschild small black hole branch end up as I added just electric potential. Well, the Hawking-Page temperature went down, down, down to 0. And the small black hole branch became the large black hole branch become the only thing there is. And then when in addition you add rotation, then once we have done enough of the electric potential, then the rotation is not enough to destabilize. The electric potential is stronger in its significance. Once we have gone up to the critical value, we're good. This has a particular significance in the context of what is called the weak gravity conjecture. The weak gravity conjecture is actually comparing these extreme limits like the m equal 3q, and in particular notices that black holes must have m bigger than or equal to 3q if there's no angular momentum. And then they wonder what would happen if m was less than 3q, and argue that there must be particles that have such quantum numbers. There must be particles like this, for which m is kind of small, so for which the gravity is kind of weak. The electric charge repulsion is stronger than that of gravity. That's the weak gravity conjecture. There must be such particles. By particles, we mean not black holes, without specifying any further what these things are. But these things that do exist will be thermodynamically favored when phi is less than phi star. At least would be in heavy competition with the black hole. The black hole would tend to be able to decay to them. However, once we make phi equal to 3 or bigger, then these guys are no longer favored. These guys that are guaranteed to exist are no longer favored. So we should not be surprised that going above 3, we greatly stabilize the black hole. And at exactly 3, we clearly go to kind of a special limit. You know, a special kind of a qualitative change happens. Yes.
To understand what is the setup. So, I mean, in terms of supersymmetric n=4 plasma, check the dependence on
This is not yet
a
supersymmetric.
billion parts Cartan value of the SO6. These are the electric charges
Yes.
and real.
And then you have an SO2, 4 that has a mass which is in the 2 and 2 angular momentum that's in the 4. So you have 6 quantum numbers, but once it becomes supersymmetric, one of them is given in terms of the others. So you're kind of in the light code. It's a null representation, like BPS representations always are.
So what is the interpretation of this critical value of
Well, so here we're not yet, I mean, well, I gave you the best I could do here. It makes the system unstable. I mean, that there are particles in bulk that satisfy this. Of course, I actually know the n=4 superionicals. I can check that there are such particles. But I'm giving a more general argument that this was not really because I was an n=4 superionicals. In some other context, it would look much the same. This is a very, very general argument that these things will greatly get stabilized when I turn on sufficiently much electric potential, external electric field. Then you see it's qualitative in nature. If instead I try to play around with the omega, the story is different. Once I make the rotation velocity bigger, we already sort of argued that, you know, it tends to get destabilized. Oh yeah, big time. What if I went all the way up to the critical angular velocity, so 1, and then say, okay, what happens when I put on the electric potential? Well, then I have here only a small black hole branch. The large black hole branch have entirely disappeared. So therefore, we have only the small black hole branch. It is true that as we go to lower, higher and higher electric potential, this minimum possible temperature, it's kind of the cusp, has gone up, up, up as omega get bigger. It reached infinity when omega got 1. And then the lower parts just disappeared when the cusp got all the way to infinity. There is no large black hole branch. And what happens to this cusp then as we go to bigger and bigger phi? If you do things in the opposite order, first do rotational velocity big, then do the electric potential bigger, bigger, bigger. Well, yes, the cusp moves further towards smaller temperature. We'd like to go to 0 temperature to get it really, really stable. But this is clearly a very dangerous direction to approach the T=0 in. The minimal temperature does in fact go to 0 as our phi is being increased all the way up to 3, but it goes to 0 in a way that's absolutely discontinuous. This is not the direction to approach the supersymmetric limit. Please go to phi=3 first, then put up your omega, or go to larger than 3, and then tune down from that side. Yes?
Sorry, does the red curve on this plot still have the large black hole?
Oh, so the thermal case, you say, or?
I just can't remember the legend, but that's still
These are all, yeah, I'm sorry, actually, this is
oh, this is all the critical velocity, and it's just the difference.
all the critical velocities, and the colors regrettably changed.
Thank you.
Yeah, good point. Good point. And the red is particularly unfortunate because it was not even a black hole before. But, yeah, well, there are only so many colors. Shades of purples. So where are we at? I've discussed somewhat the thermodynamics of these non-supersymmetric black holes and tried to argue that, yeah, the critical value of the angular velocity is 1, and it tends to destabilize. The electric potential has critical value of 3, and it has this stabilizing effect. So now we turn to the thermodynamics of the supersymmetric black hole, where we are exactly at the critical limit for both of them. And those are kind of like all by themselves very special. They would sit in the extreme corner where the free energy is 0, the temperature is 0. They are a point. They're not even any of the curves in this special case. They all collapse to their sort of only being cusp. And then we want to use a microscope and see, wonder what happened in there. So first, we even have to address the conceptual issue. What are we going to do, by the way, when the potentials are all at a particular value, the temperature is all at a particular value of 0? We don't have nice graphs because it's a point. Well, we introduce what we call the BPS potentials. We think about saying, well, actually, I say that I want to go to 3. Let me go a little bit away from that, preferably from on top. And let me also make the T a little bit different from 0, positive, and take the ratio. Similarly with omega. These primes here then I might think about as actually differentiation with respect to temperature. It's computing the thermal derivative. So in that sense, I would say we really do work at exactly T equal to 0 and phi exactly equal to phi star, but the approach to that, we have a number of different possible approaches called derivatives. So we are at the limit, but the derivatives here do have specific values in the limit. And those values we can use to vary. The corollary, I should notice, by the way, because that's going to play some role, is that the convention here, because I really want the prime to be derivatives, else I would be confused about the signs, that since omega can only be smaller than omega star, our omega prime will always be negative. It's too bad that we have sort of a chemical potential that's by definition going to be negative, but I can't help it. Speed of light is an upper bound. It's just how it is. Think about this from the stat mech kind of side. The partition function would be adapted now to the mass equal to be a very special mass. So we have some kind of partition function here. And we would say, oh, instead of having just a beta m like we normally have for a partition function, let me subtract off the m star and think about it as the excess energy over the BPS limit. And then weigh these things here with their departure from their critical values. Then as t goes to 0, we get exactly this kind of function. Our parameters that are conjugate to j and q are omega primes and our phi primes. We just lost the temperature in the process. I should also notice that at linear order and temperature, you can do the Legendre transform of this function here and see that all you learn is that the mass is exactly equal to the critical value, the m star. So that means that even though I say go a little bit away and then study the limit, you might think, oh, you mean nearly BPS? I did not mean nearly. I meant exactly BPS. These prime variables do not study the approach to the BPS. They have absolutely no information about anything that is away from the surface. It's interesting to also consider the next order, but we won't in this talk. Actually, we will a little bit. But so this is the underlying stat mech, and it sort of can be made rigorous, especially if there's a gap here, which there is if we have enough supersymmetry, but that's all good. So, as I say, the BPS black holes have free energy, 0, identically. At linear order, the free energy will give that m is equal to the BPS mass, because that is what we're interested in. It tells us absolutely nothing more. So the conclusion is that the BPS thermodynamics is kind of projective. We can think about everything as being proportional to this T, and then consistently divided out. It means that we have a homogeneity property. And it's that homogeneity property that is equivalent to the BPS condition, and therefore the dividing by T, we can see, is really just choosing coordinates on a projective thermodynamic manifold. So even this whole thing that I said, let me take T going to 0. Actually, let me take them all going to 0 at exactly the same rate, and which ones I consider the ones that are somehow the temperature or whatever is just a matter of convention. We have projective thermodynamics. So we lost one variable because only ratios matter. That's what m equal m star means. Only ratios matter. The first law of the BPS black hole thermodynamics now is going to be that the free energy in these thermal units is going to have differentials. That's going to give us the charge and give us the angular momentum. So therefore, the BPS free energy is going to be a function of these prime variables, and its derivatives is going to be the charge and the angular momentum. So it works just like a normal free energy, except there's no temperature. And just like the normal free energy, if we did a Larsen transform, we could find the entropy if we felt so inclined, but I'm mostly going to do free energy as function of potentials rather than the corresponding entropy as function of charges. So what would temperature then be? Well, the temperature was 0, the physical temperature. But normally we have an intuition about temperature that somehow when we put temperature on, if you go to very high values of temperature, somehow there's a lot of states, there's a lot of energy, something like that. So we can wonder why, how would we manage to get highly excited states? This actually is in the opposite direction. It's when the omega prime itself, say, goes towards 0, or when the phi prime goes towards 0, we tend to get highly excited states. We tend to get a lot of free energy. And therefore, we're going to try to think about these values as themselves being analogous to temperature. So the physical temperature here would be large for highly excited states, we have large free energy, and also physical temperature normally is positive. Motivated by those things, I'm going to define very heuristically, but just in order to get better intuitions, a BPS temperature. The BPS temperature is going to be 1 over the rotational frequencies with a minus sign because the rotational frequencies are always negative. Therefore, this quantity here is definitely always positive, just like a true temperature. And it will have the property that as these omega primes here get small, this temperature gets big. As they get small numerically, close to 0 from the negative side. This one here will blow up, and there'll be a tendency that the black hole we expect to become sort of more unstable or something along those lines. We can think about there being a conformal regime. So this is when I have now explained what did I mean by this diagram. Well, the free energy here is the BPS free energy. Think about it as saying, oh, free energy was 0, but in thermal units, it was something. This tau here, well, temperature was 0, but this one here is the 1 over the rotational velocity. So as you go really, really close to the speed of light, as in even in the thermal units that go to 0, you're that close to the speed of light, super close. You go to high temperature. Is when you not only are at the speed of light, but you sort of have approached the speed of light preferentially in going first towards the speed of light. That's something that we know could be very dangerous. It could be something that could destabilize, and therefore you should not be so surprised perhaps that there's an unstable branch up here because it corresponds to having given preference to taking the omega going to omega star over the phi going to phi star, at least differentially. Is there a question? But we're still stuck, of course, we haven't actually learned anything, that the phase diagram is strikingly similar to the AdS worship. And that is part of why we want to develop this whole thing in a more systematic way. Yeah.
And so here the definition of BPS temperature is 1 over omega prime here, omega prime here. Intuitively, it seems when omega prime tends to 0, the physical temperature tends to 0, right? So
but as I say, the physical temperature is just, don't think about it. It's set to some units, everything is projective. All we're talking about here is that you should wonder whether I give preference to the omega. It has to be 1. But what order did I take things in? Did I really emphasize an omega goes to 1 linearly in the temperature, phi goes to 3 linearly in the temperature. You don't have a choice, but you still have a choice with their relative speed.
Oh.
And then if you somehow say, no, omega wins, that is high temperature. So it's a subtle thing. It's still somehow saying, yeah, that got closer to the speed of light than phi got to 3, even though, well, they were both equal to that. It's true. This is how differential calculus works. You take the derivative at the point, but the derivative tells you how fast you got in, and it is meaningful to compare derivatives.
I guess just to be extra clear with this, so we're saying that all these different ways of taking limits are all valid, but they might give different results, but they're all okay.
They're all valid. So there's a space of supersymmetric black holes,
right,
as there should be. They have different values of charge and angular momentum. They all have their mass given by basically the sum of q's and sum of j's. So there's no temperature at tau. But there is a choice of, okay, you want these to be mostly charged or mostly angular momentum, or how do you distribute these things between these two? I mean, that's sort of how chemical potentials work. And that's what the prime variables allow you to do.
Actually, so I think the basic idea is just how to, the way you choose to approach the singularity, just different path.
Yeah, the space of different paths. This is why I'm saying it's actually projected geometry. It's the ratios of all the variables. That means that the number of derivatives you have agrees with the number of variables. This was not special to AdS5 because S5. It's simply a feature of how to describe thermodynamics on the surface, not a wave. It's on the surface, but you can think about it as a feature of the limit, how you got there.
But it is somewhat counterintuitive that when you go to small velocities, you get high temperature.
But it's not small velocities. Small here means very, very near the speed of light. So they actually are very big. Right?
Or you're only in the region.
Yeah.
close to
Omega
zero.
minus omega star is going to 0. So they're going towards the speed of light. And then tau big actually means they went to the speed of light really quickly. More quickly than you tuned your potential. Something that's potentially destabilizing, although it's not totally clear how that works in this limit, but this illustrates then, okay, so how does it work? And actually there are two ways that it can compete. This one here is destabilizing, as you might have thought, but there's a way out. Go down here. And that's a different branch, and that's a different, so there actually were two options. And so these diagrams here, the AdS5 and the AdS4, so they're similar. Certainly visually they look similar, but are they actually the same? Well, the high temperature behavior. So on this small black hole branch, when we have basically what was sort of like AdS4 chill, but we go out towards very high temperature, this free energy, the original one actually went like tau to the minus cubed. My W here goes like tau to the minus cubed. I defined these things, the omegas, the W with taking suitable derivatives of tau in such a way that this is true. This still is true just by the homogeneity of the free energy. But given that, we can go down and see what happens on the large black hole branch, which actually is what we're mostly interested in. Well, there the high temperature behavior goes like T cubed for the standard n equal 4 super Young mills. That's actually what follows from conformal symmetry. But the BPS free energy goes like tau squared. So they're not the same. They look the same because they sort of qualitatively are the same. Who can tell the difference between a quadratic and cubic? Just look at these graphs here. Well, they are different. The lower one was different. What it means is that the large BPS black holes, they behave more like a gas in 2 spatial dimensions rather than 1 spatial dimension. The fact that we had originally a 4-dimensional quantum field theory, but we are now projecting into special values of charges. So we have in the process apparently projected essentially a dimension out. It's to do with these J's. The spins have to be aligned, and that makes somehow missing a dimension. And that's a feature of the corresponding limit in the microscopic field.
Sorry, but the way you're talking about this, you're making it sound like we should really think of W as if it were a free energy, right? Because then you say it's but what reason do we have to believe that?
It was the partition function Z. It was log of C. It's true that normally you say, oh, wait a second here, log of C, is that really the free energy? No, shouldn't I also divide by beta or something? Yeah, you should. Here, I didn't. That's the difference. Right, so it's basically both of them log of the partition function. It's just like, oh, should you divide by T or not by T? Well, when you don't have a temperature, you can't, so don't. But it is just the log of the partition function. And thinking about that as a free energy is pretty much the best you can do when you have a statistical mechanical system. Is that you weigh everything you have, Q's and J's, with regard to appropriate chemical potentials, and you sum over all the states. That's the partition function. I'm calling log of that the free energy. I mean, what am I supposed to do? That's reasonable, isn't it? Even if I didn't actually divide by temperature.
That part is a bit important though, because
No,
it's not a coincidence that you have to do that. I mean,
well, but
the states. And,
well, so I say anyway. So it has the I defined it via my first law, right? That the dW had a minus Q d phi prime, just like the dG had a minus Q phi. It does. So they looked I mean, you're saying it's not a coincidence, you're correct, but I'm telling you that this projective geometry does exactly the right thing in readjusting. You want to not divide by the same thing. In order for now, if you Lissano transform, for example, and figure out, okay, that's a free energy. What's the energy? What's the mass? Well, you don't want that to be an interesting answer. You actually want that to be the sum of Q's plus the sum of J's. Because I did not divide by the temperature, I actually get exactly that. It means that my energy was not interesting. I don't want it to be interesting. It's supposed to be equal to something that's just made of the other guys. So this homogeneity property, the projective part, makes this the right prescription. That's kind of part of the point. You know, not obvious maybe that that's true, but it's actually what you normally would have done if you had a stat mech system that didn't have any temperature, just have magnetic fields or whatever else. You might write on a partition function like this. I mean, so what we actually have, these BPS black hole free energies, is that we have some, again, parametric representations. Our W is actually a potential function of these various prime potentials, but written in terms of some obscure A's and B's. And well, these are prime potentials are themselves solutions to some constraints now. So I want to think about these A's and B's being functions of all the omega primes and phi primes that you get by solving these two equations for two variables, then plug in there. Then we get a well-defined function in terms of W, in terms of all these various phi primes and omega primes. And we say, go plot.
So I should have asked earlier, but explain what is the definition of this? Like, what is the meaning of these two angular velocities from the point of view? I think about it.
We're in five dimensions. So
no, like I think about this holographically, just as a plasma, some kind of.
So in the n equal, you mean in the n equal 4?
Right.
There we have an R symmetry group. That's
so one of these is around this 5, right? So,
no.
Oh, they're both no.
They're
This
both, no,
space time, right? This one not around this
no. I mean, so we have on the n equal 4 is n equal 4. It's a thermal n equal 4. So we on a so just from the field theory side, 3 dimensions, we have kind of a Euclidean circle S1.
Right.
And we have a 3 sphere. We've got our theory on a 3 sphere. That 3 sphere has a SO4 rotation group, which is SU2 plus SU2. So therefore, you know, a 3 sphere has 2 angle momentum.
That's because we are
2 sphere. And so 2 sphere has 1 angle momentum, but a 3 sphere has 2.
Okay, because our space is really on a sphere.
On a 3 sphere, yeah. So otherwise the algebra works just like our Fermi guy. Right? Okay. So we have some parametric plots here, and I show you these obscure formulae in part actually by pointing out that there's something slightly wrong with these formulas. They depend on only these 2 parameters, A and B. The 3 black hole charges have, as we took the limit, lost an extra variable, not just the temperature, but they lost another variable too. The 3 black hole charges are functions of 2 parameters. It's fair enough that we used to have a mass that was independent, and then the 4 charges, if you think about mass as a charge, were a function of 4 parameters. But somehow, as we take this limit, we lost 2 parameters, not just 1. What this means is that we are only able to go to the supersymmetric limit when the various charges are not independent. The Q's and J's must be related by this totally obscure relation. If it's not related by this relation, saying, look, but I just want a black hole that has this Q and this J, what's wrong with that? Well, if those Q's and J's don't satisfy this, you cannot find a supersymmetric black hole with that particular set of Q's and J's. Sorry. I mean, you can ask for it. It seems reasonable. And on the field theory side, you certainly have states with any Q's and J's that are supersymmetric. But on the black hole side, you don't. Just don't.
There's no direct map from the holographic dual to the gravity theory.
There's no what?
So there's no map between one geometry and one quantum field theory on the other side. I mean, there are many.
Right.
There are many
So
quantum field theories that.
You have configurations inside your n equal 4 superunimals. You can check configurations that appear to have quite a lot of states. In fact, have n squared kind of many states. And you say, oh, that should be dual to a black hole, right?
Yes.
Nope. Even in a supersymmetric sector. if you did not satisfy the appropriate relation, you cannot find such a black hole. Sorry. The feature of the holographic map. I didn't say this was obvious. You're supposed to have known. It was not in the AdS5 dictionary you have learned. It is the, oh, wait a second, that must have been one of the footnotes, or not. It's not by the book, but it is a feature.
Yeah.
Sorry, could you please explain again where does this constraint?
Why is weird?
No, where does constraint here?
Oh, it came from, it just came from, I take my actual geometries, and I had many of them. I had one for each mass, charge, J, and momenta, and I take the limit where I went to zero temperature. And then I just noticed to my bewilderment that even though I only tuned one variable, actually I ended up tuning two, not on purpose, but that's what I did. Mechanically, the way it works actually is that the variable you want to tune to zero turns out to be the square of one variable plus the square of another variable. So whether you want it or not, you tune two. And I'll show you that in a second. Whether you want or not, you tune two. You don't have a choice. So one way to look at this surprise is that there are two distinct ways of breaking supersymmetry if you don't like supersymmetric states. For example, you could say, oh yeah, this temperature equal to zero, that means extreme black hole. That is what happens when we have the lowest mass for any given Q and J and so on. Called extremal mass. When I'm at the extremal mass, same as zero temperature. If I then go above the extremal mass, non-zero temperature, I break supersymmetry. But there's another way of breaking supersymmetry. Namely, say, look, don't increase above the extremal limit. Change your Q's and J's so they no longer satisfy the constraint. Your supersymmetric black hole did satisfy the constraint because else I couldn't find one. Now let me consider Q's and J's that don't, that are a little bit different. Still extremal, still zero temperature. It is not supersymmetric if you violate the constraint, because that's the reverse of saying if you have supersymmetry, you must satisfy the constraint. So there are two different ways, and you can ask, oh, this new way, what direction does it correspond to? It corresponds to this direction, a particular combination. And it's a combination that we kind of know that yeah, this was the one there that we kind of like being positive. These ones there we kind of like being negative. So it's kind of a combination. The reason the relative signs is that this is the likability factor, that this is the one that, somehow was a measure of how unstable these things are. So the excitations above the BPS limit, if we increase the black hole mass away from supersymmetry, then we can get some Tsquared excitations. This is actually the heat capacity and so on. There's an interesting story about this thing. This is not going linearly away in the temperature. So this describes truly away from the supersymmetric limit. Ligo quadratic is an interesting story. So it's described by the Schwarzschild theory, near AdS2, CFT1, SYK models. There's an entirely different talk there that I won't give. Only thing I will say about that story is that, yeah, there were two different ways to go away, temperature or violate constraint. And they actually have the same coefficient. Whatever coefficient this is, which I haven't written down, it's the same for the two. So kind of like adding temperature, let's go away from the right mass, or violate constraint, equally expensive. The cost the same. And in fact, that can be shown be due to broken supersymmetry. We are away from supersymmetry, but supersymmetry is strong enough that it will relate these two different coefficients. So this is spontaneously broken in equal to supersymmetry to relate the two. And there's an interesting story there. Yeah.
What does
There
it
is
mean?
another method to break supersymmetry, at least it's clear in the field theory side, and that is if you take this Euclidean time direction and impose the antiperiodic boundary condition on the fermions, then
Yes.
we know that this n equal to 4 super Mills will translate into an ordinary n Mills, in fact, in one less dimension if the circle
Very good.
is
Very,
taken.
very, very
The
good.
question is, how do you see here in this?
This is exactly what this is related to. Yeah, I'll tell you. You're right, this is related. This is related to that insight that you have there, is that you have a very special boundary condition that you want, or else it doesn't become supersymmetric. It was perhaps not part of what you thought about at first, but
But is
But
it
yeah,
true in the side of the black holes, what happens?
yes,
So
yes, yes.
in
So
the
I
field
think
theory, I understand what, but how do you go from this supersymmetric black holes to the non-supersymmetric ones?
I will show a formula that does the best that I can. It's not as good as I want to do.
But so from the point of view of just again field theoretic plasma, what
Yes.
is there? What is it meaning of this direction? So I can heat it up.
You can heat it up,
Yes.
or you can you can, well, so yeah, I would say so. There's a Wilson line. I think I do have a. Don't I have a? Yeah. So this is the interpretation. So what we can think about is first in terms of limiting procedure. We want to go to where the temperature is zero. It has to be. This thing also has to be zero. It was made out of guys that we're going to zero, but the ratio could be anything. So in principle, we don't know what this thing should be. So how do we interpret it? Well, we interpret it as the phase of the supercharge. These are all supersymmetric black holes. But once we say, look, I have a supersymmetric black hole here. Yeah, it's preserved by what supercharge? Now I have a different black hole that still is BPS, still supersymmetric. It has the right mass related to charges, but that other relation is guaranteed by a different supercharge. From the point of view of the first supercharge, we're going to say, oh, you broke supersymmetry. On the other hand, from a more global perspective, we say, no, I didn't. Once I'm BPS, I definitely preserve supersymmetry, and I don't have a preference for which supersymmetry I should preserve. So this is the story, is that our phi prime is parameterizing among the various supersymmetries that you might wish to preserve. Here we just from the black hole side say, well, take a supersymmetric black hole. We didn't say which supersymmetry, because we had a lot of supersymmetries. We broke some of them just by the fact that the black hole, translational variance, all sorts of things, it definitely breaks. But it has different options for what exactly it breaks. And this ratio here says there's a one parameter set of families about exactly which supersymmetry is preserved, and depending on which one, at different values of phi prime. The field theory doesn't like such a thing. It says, no, in the field theory, I have a certain, in my low energy effective field, there are certain preserved charges. Don't mix them. They correspond to different vacua. You can't do that. Yeah, okay, but with the black hole, who did it? And I don't have a choice. This is what it did. Yeah. Oh, yeah. Not a question. So the dependence on this phi prime, people say, oh yeah, maybe this doesn't depend. Oh yeah, it does depend. This, if you take phi prime negative, which actually seems like the bad direction, the one that seemed a little bit suspicious, but there are black holes like that. They're perfectly regular. And no, sorry, I shouldn't say they're black holes like my free energy. I can evaluate for any value of this phi prime, and what you find is that this small black hole branch has a funny asymptotic. It's a funny asymptotic. And then the larger phi moves the cusp lower down. So as we expect, maybe this phi prime bigger, as in smaller, less negative, has a stabilizing effect. And then once it goes positive, then actually there simply is a maximum tau here. So the omega prime, which is dangerous, making omega prime really, really big. Now that I made phi prime positive, it just can't get all the way to its limit. So therefore, there's an absolute maximum temperature. And as I make phi prime bigger and bigger and bigger, it gets more and more stable. And in the limit, when I make phi prime really big, they're only large black holes. So I have a phase diagram as function of that phi prime. It's reminiscent of some of the phase diagrams that we had for the non-supersymmetric black holes. It's an interesting parameter, and it's one that we can analyze in the field theory side. But the physical significance, as I say, is actually quite obscure. We have this first law of thermodynamics, or black hole thermodynamics. These Q's and J's really are distinct physical parameters. And the W here depends on these guys independently. I must be able to take derivatives with respect to phi prime and omega prime independently, else I can't recover my Q and J. Except that there's a catch. It must be those Q's and J's that I get once I take these derivatives somehow satisfy the constraint. And then saying, oh, how do I implement that? the potential here, the novel potential is the conjugate variable to that constraint. So that is what it means from the sort of thermodynamic point of view. From the index point of view, which is how people usually analyze these things in the microscopic theory, people there does something totally different. They would say, oh, let me actually insert a -1 to the F to weigh everything by the fermion number. That's what we kind of could do to make things supersymmetric. It's not true that all states must satisfy this, but there's a way of counting supersymmetric states. And importantly, it's a way of counting it in a way where it becomes independent of coupling. So you can go from strong to weak. And in this formulation, the partition function becomes independent of the phi prime. But the black holes are different. They're in the strongly coupled regime. And there I interpret phi prime differently. I interpret it as saying that, look, there was this phi prime here that you omitted. You omitted it because this was defined with respect to a specific supercharge, this fermion number. But I could have used the other supercharges. They were just as good. These are just different sectors in the same quantum field theory. They're perfectly legit. You should take them seriously. However, what the black hole apparently does is that it considers all the different values of the supersymmetric states, and then it takes an equilibrium value. This is different from having something that's independent of phi prime. It's something that does a specific value of phi prime. This is something we understand very, very well in the CF2 context. The CF2 context, the chiral primaries are the supersymmetric states. What you count in the index is what's called the elliptic genus. You take any supersymmetric states, comma, anything on the other side. What the black hole does is that it doesn't take any supersymmetric state. It takes a specific supersymmetric state. So it does things differently. The black hole does differently from the index, but they both sort of lose a parameter. The index loses it by just having something it is not dependent on because, well, you just didn't put it in because it didn't commute with the supercharge. But there's a technical reason that you weren't able to put it in. But the black hole then could have depended on that parameter. But cleverly, it doesn't. It averaged over that parameter. So the strong coupling behavior, I interpret in that way. So these are my main results. The AdS black holes and AdS5, they're strikingly similar to the AdS Schwarzschild. In this talk, I've entirely focused on the black hole side, the thermodynamics. Only very briefly, referred to the field theory side, but of course, there's a total story there. There's also other stories on, as I say, the approach, the near AdS2 story. But here, I particularly emphasize the projective thermodynamics as simply an idea to describe phenomena like this. And particularly emphasize this potential phi prime that has a central role that can easily be overlooked. So thanks for your attention.
We have time for some questions from the audience or from Zoom.
Yeah, this is a really naive question. I'm sorry, but I'm just kind of wondering, like, what are like the applications of these results?
Well, so the applications would be on the other side, that I have this quantum field theory that I'd like to study. I can study it freely. Once you turn on the coupling, you can study perturbatively. When it becomes really, really strong, you don't have any idea. And then, yes, you can take some quantities that will be constructed carefully in such a way that they're dependent of the coupling. So you can learn a little bit about what happened with the strong coupling. Or else you use AdS-CFT correspondence. And I would say, that's what I do. I get the answer, a strong coupling to a question that I didn't know how to do in the field theory side. And it seems like a strong coupling. In fact, the way I think about it is that these various supersymmetric states, they can combine without breaking supersymmetry. They can split apart. And what happens, a strong coupling is that they do that a lot. And then equilibrium happens. Okay, that actually makes sense. Once you have things a strong coupling, then states mix a lot. And what happens as a result? Equilibrium forms. So effectively, you can't have as many charges and angular momenta as maybe you thought you could, because equilibrium has formed. It's not that there were no states at all of these other, or even there were a lot. But even when you have a lot of states, thermodynamics is thermodynamics, it kind of finds an average. So I have interpretations of this on the field theory side, right? And that's why we do this kind of thing, is to understand things clearer on the field theory side, where we had, here there were some confusions, but there are worse confusions on the field theory side. So, this helps. Yeah.
So my recollection that when one considers the states with large charge, there quite generically there also appear new phases which are kind of correspond to some striped phases when it's not spatially homogeneous.
Yeah, that is true.
Are they playing a role here? Those also might be supersymmetric, right? It's possible to break some of translational invariance, but it's not.
Maybe I do not know if such things are, if there are such things that are supersymmetric. I believe not. I mean, I believe that, I think that these are all the supersymmetric states. All on the gravitational side. I think that, I think the way these black holes are constructed, that really is how we say, look, let's assume there's a spinner. Now let's form bilinears, whatever that means, that I must have certain rotation or certain symmetry, certain killing vectors, and so on. And this way, and I don't think I can get striped phases consistent with supersymmetry. But that's a very good question. Very good question, and I certainly would think about some aspects of this in the language of sort of the AdS5, which is the kind of thing we're talking about. That it's richer than you might have thought at first. And here it's possible that I don't have the full phase diagram. There are surprises somehow that have been overlooked. Yeah, but I don't think we put it in by hand. I don't think we put it in by hand.
All right, could you go to the first slide of the phase diagram? Just non-BPS. So, are there any reason why such kind of the cusp is so sharp in this first one picture? Why is it that, very continuous chain, but very sharp?
Well, why is it so sharp?
Yes, why is just the first order?
Well, I don't quite know. You're saying it could be second order?
I don't know. I just look at shape.
So there are variations of this. In fact, if I had done other things, you can turn this thing into more like well, for this question, it's not as sharp as it looks. It's actually, it would look much smoother if I went to a different ensemble. If I went to, so this is Gibbs free energy, but if I actually went to the ordinary free energy, it would help. So that's the best I could say. It's actually not, this here, as it stands, is actually not, the most interesting part about this is that there's a minimum temperature. Not so obvious that the black hole would have a minimum temperature. For your Schwarzschild black hole in flat space, you had any temperature was possible, but here there's a minimum one. That's the surprise. And I would say it's actually pretty smooth if you look at, for example, the temperature itself as function of a physical parameter. Here it looks like the temperature somehow is very cuspy. Well, it is just a smooth minimum as function of the mass, for example. It's just a smooth minimum. So the more interesting part actually is you can turn it into a second order phase transition, and by turning on more parameters and so on. But that I haven't pursued, both because others did it a lot some years ago, and it is inconsistent with the supersymmetry. It all sits up here. And the supersymmetry ultimately has to do with how do we approach here. And so this extra structure that I could get and that is interesting, it is sort of not interesting for me because it's inconsistent with the limit I try to study.
Yeah. And also, I'm kind of confused the way you come to this is just the one parameter evolution along the line. When you go to the answer comes the way you go to T, HP, which branch will they choose? Will they just go directly to thermal, or they will also go in the blue line?
I don't quite understand.
Yes, when you go to this point, will the evolution just go along the red line?
From the point of view of me actually having some geometry, just write down some black hole that looks vaguely like a Schwarzschild black hole, but a bit more complicated from what you've seen in the GR class. And I simply say, okay, let me start with this parameter, the AdS length, and just tune it relative by keeping the others fixed. Well, I get something that literally looks like a Schwarzschild, and then it changes a bit, and you're like there. This does not, from that point of view, look like a particularly sharp thing. It just that it was written in these parametric forms, remember? So therefore, your black hole solution, it actually had some of the physical parameters for solutions to quadratics. So quadratics have two solutions. So at some point you get to the minimum possible when the derivative is 0. And this one here looks like absolutely nothing special in the solution. The only thing there is that, yeah, but if you think about this from sort of a path integral point of view, which is how we normally think about AdS5 correspondence, is that, look, we have particular boundary conditions at infinity. There's particular boundary conditions. They are given at infinity, and we should take anything inside. Anything inside is allowed. The quantum theory, literally everything. In the semi-classical theory, all saddle points. Okay, which saddle points do you have? Well, I have my black hole saddle points. They solve the equation of motion with the correct boundary conditions. But then I also have another saddle point that basically corresponds to me just having put constant potentials on. But nothing really happened. So I didn't put in a gravitational solution. This was sort of flat space. But it was a solution. The question is just, does it have bigger or smaller free energy? And the boring one had no free energy. And that seems like something that is not that special for the black hole. The hitting 0 doesn't seem that special.
I mean, just when you turn down the parameters, so which one would they choose? I mean, or
well, there, I mean, we think then that in the quantum theory kind of perspective, we think that, well, look, I mean, the one with the lowest free energy is the most stable. All right. But it would be so, but is there a free gas here also? Yes. However, it should be possible for it to tunnel down there. And the tunneling amplitude would, so, but I mean, this could be non-perturbative. It's not like black holes are formed just spontaneously, just like that, right? But it is thermodynamically favored. And the thought would be that it's because there are lots and lots of them. You have lots and lots of microstates. That's why even though the tunneling amplitude is small, the phase space is huge. So therefore it's favored. But I mean, do we understand that thing actually, detail? Nope. AdS5 correspondence gives us a machine that tells us how to compute the free energy. And then we try to interpret it.
So let's thank him again.